So in the last video, we've seen how we can use a differential amplifier like what you see here in order to get rid of a common mode noise, for instance, environmental noise from mains power or really anything else. It could be motor noise, could be motion artifacts from the animal, anything where you can have a reference signal that picks up the noise, but not the signal of interest. In theory, a differential amplifier like what you see here is great for that. In practice, as you see here, the amount of current that this thing is drawing means that we're massively distorting signals or eliminating signals, as you can see by the voltage drop across these resistors that are stand-ins for tetrodes, for instance. Our input impedance, you would say, to this amplifier is lower than we would like because we're drawing current here. How can we solve this problem? Basically, we're in the same situation as we were right at the beginning of the course when we thought about just connecting a tetrode to a long wire, where we saw that the wire alone had enough input impedance to distort the signal, and we used a buffer op amp to amplify the signal's current driving capacity to drive the cable. So why don't we do the exact same thing here and just buffer the signals before they go into the differential amplifier here? So to do that, I'm just going to grab two op amps. And so here I'm going to set them up in the non-inverting configuration. So one of them is the plus on top, the other one is the plus on the bottom. That's just for aesthetics. And then we need to wire them up with negative feedback because we just want buffering out of them. And so now we have a two-stage system where we have a pair of unity gain, non-inverting buffer op amps that have extremely high input impedance because their non-inverting input terminal is connected directly to the tetrode. And their output now goes to the differential amplifier. And the differential amplifier takes care of the common mode rejection. So let's see how that works. And you can see that we're getting perfect 10 millivolt spikes out of here, and we're not drawing any current from the input. This is basically the idea behind an instrumentation amplifier. So now let's very quickly go over some details of how to set something like that up in real life. And by the end of this, we should be able to understand how to use the instrumentation amplifier chip that comes as part of your kit. So far we've seen this topology with two unity gain buffer op amps at the input and the differential stage at the end. So let's begin by adding a little bit of gain to this, because we don't just want a one-to-one signal with a 10 millivolt output spike, but we want to bring that up into something that we can digitize. Okay, so I just rearranged things a little bit here. And so now let's add gain to the buffer input stages here. As before, we will do this by just adding a voltage divider to the negative feedback to make the amplifier work proportionally harder to get its input terminals to the same voltage. And so now with a one-to-one voltage divider, we see that we doubled the gain of the whole system by making the buffer input stages that were previously unity gain into a gain stage. In theory, this could work, but now let's imagine that these are physical op amps that have slight imperfections. So for instance, let's imagine that these resistors here are not perfectly matched. So I'm going to take this resistor, and instead of 1K, let's put 1.1K. That's not a huge difference, but we can see that we created a huge problem, which is that our entire output signal has now been taken over by the common mode noise again. And this makes sense because the entire trick of the system previously rested on the fact that if we had the same signal on the common mode here, that it would create the same voltage on the input terminals to the differential amplifier in the end, and that those would be subtracted out. And if the gain now between one and the other is not perfectly matched, then we have a problem. So how can we solve this? There's a very simple little trick here that really amounts to just getting rid of these voltage dividers between ground and the feedback for the two input stages of the instrumentation amplifier, and instead just connecting them together so that one can serve as the reference for the other. So let's just see what happens when we do this. So now, magically, everything works again, and we get gain, but we also get perfect common mode rejection. And so let's take this a little bit further and really mismatch these things. So I'm going to put 2K here. And now my gain has changed a little bit, but somehow, even though these resistors are now as imprecise as they can be, the common mode rejection ratio is still perfect. There's another nice thing that happens here, which is that there's this one resistor in the middle here that if I, let's say, mate that resistor so that us as users, we can change it, we can use that to change the gain. So I just set it to 2K, half the gain. This resistor in the middle that's highlighted now is commonly known as the gain resistor. And on the instrumentation amplifier that comes as part of your kit, this is referred to as R gain. And that's the one where we get to pick the amplification gain of our instrumentation amplifier. But for now, let's just go through a simple schematic overview of why this topology does so well. So let's consider the case of us having only common mode noise from here and here. And we want to understand why under no circumstances can this common mode noise elicit a voltage difference on the inputs to our differential stage. To understand this, we literally just need to follow the current, and it's going to become relatively obvious. The first thing that we know is that because of the feedback on these input op amps, the voltage on the positive and negative input is the same, which means that if V1, one of our voltages, is the same as V2, which is the basic condition for it being common mode noise, then the voltage is the same here, and then the voltage is also the same here. And we know that there is no current flowing in and out of the inputs of the op amp. So there's no current flowing around here. Similarly, there's no current flowing around here. So if there's no current flowing here, that means that there is no voltage drop across this resistor, and there's no voltage drop across this resistor. And so assuming that these resistors are the same, the only voltage drop in this whole loop here is now induced by the voltage differential between V1 and V2 across our R gain. So if V1 equals V2, then the voltage in this loop, because there's no current here, is 0, which means that assuming that our gain stage is matched, which is an easier task because now we're dealing with an amplified signal, we get a very good common mode rejection. If V1 is not equal V2, now we can understand how much voltage differential that is inducing in this loop by just looking at our gain. And so if you want to understand this in more detail, have a look at the handout. There's links to more in-depth documents, and you'll find a lot of material about this online. But this is the basics of what makes an instrumentation amplifier so great. So now that we've seen this, I'd like to show you one more little scenario that explains why we would want high input impedance on our amplifiers. So let's go back to a simple differential amplifier that, as we've seen, has pretty terrible input impedance because of all these voltage dividers here. And consider what happens when we have actual electrodes with their own impedances. So now we're in a situation where not only do we attenuate the signal quite a bit, but also because of the terrible input impedance of the amplifier, we have another problem. And that is if our, let's say, tetrode has a 300 kilo ohm impedance, but our reference screw, let's imagine this up here is our reference screw, has not 300, but 305 kilo ohm, what happened? Not only are we dropping the signal across this electrode resistor here because of our input impedance, because of the current we're drawing, it also now matters a whole bunch how much we're dropping, what that impedance is. So if our reference electrode is not exactly matched to our recording electrode, we're not able to see the common mode signal across those, so we cannot subtract it out. An actual ground screw might look more like this. So now we have a problem. Now we can look at the same situation with our instrumentation amplifier. This is obviously an idealized version of one with absolutely no current running in. But now we can take these 300 kilo ohm electrode impedances and do whatever we want with it because there's no current flowing in, so there's no voltage drop across the electrode impedance. So we can have an extremely low impedance reference and an arbitrary, theoretically, tetrode impedance and still get nice common mode rejection. So that's another reason why high input impedance matters.